Picture a time when the world of physics was in turmoil, when the foundations of classical physics were quivering under the weight of new discoveries. It was the dawn of the 20th century, and the comforting, predictable universe that Newtonian physics had described was starting to show cracks. Out of these cracks sprouted a new, strange theory that promised to unlock the secrets of the microcosm: quantum mechanics. This nascent theory, with its radical propositions, was like a turbulent sea compared to the calm pond of classical physics. It proposed a universe where particles could exist in multiple states at once, where uncertainty reigned supreme. It was a bold, daring step into the unknown, a departure from the deterministic worldview that had held sway for centuries. This was the stage upon which Albert Einstein, a scientific giant, would leave an indelible mark. Enter Albert Einstein, a man whose genius would redefine our understanding of the universe. With a mind that dared to venture where no one had before, Einstein unveiled the theories of special and general relativity, taking science into uncharted territories. His theory of special relativity, with its profound concept of space and time being interwoven into a single continuum, challenged the very foundations of classical physics. Next came the general theory of relativity, an audacious proposition that gravity was not a force, as Newton had suggested, but a warping of space-time by massive objects. This theory not only revolutionized physics, but also laid the groundwork for modern science, paving the way to understand the universe's most elusive phenomena, from black holes to gravitational waves. Yet, despite his groundbreaking work, Einstein harbored deep reservations about the emerging field of quantum mechanics. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper that would challenge the very foundations of quantum mechanics. This groundbreaking paper introduced what's now known as the Einstein-Podolsky-Rosen paradox, or the EPR paradox for short. The EPR paradox was a thought experiment designed to question the completeness of quantum mechanics. Einstein and his colleagues proposed that the seemingly random nature of quantum measurements could be explained by the presence of hidden variables. In other words, they suggested that there might be an underlying deterministic order to the apparently chaotic world of the quantum. To illustrate this, let's imagine two particles that have interacted and then moved apart. According to quantum mechanics, the state of one particle is instantly connected to the state of the other, no matter how far apart they are. This is known as quantum entanglement. But Einstein, Podolsky and Rosen argued that this spooky action at a distance was not only counterintuitive, but also suggested that quantum mechanics was not a complete theory. They instead proposed that the particles carried hidden variables, or additional information, which determined their states from the outset. This meant that the particles were not really influencing each other across space, but were simply revealing preset properties. This view supported a deterministic universe, one where everything happens for a reason and nothing is left to chance. This notion of hidden variables was a direct challenge to the orthodox interpretation of quantum mechanics. It suggested that the quantum world was not inherently probabilistic, but instead followed a deterministic order that was just not yet fully understood. In essence, the EPR paper was a manifesto for determinism. It was a call to arms for physicists to look deeper, to seek out the hidden variables that would make sense of the quantum world. The EPR paper ignited a debate that would send ripples throughout the scientific community. It would also set the stage for one of the most profound and fascinating scientific debates of the 20th century, a debate about the very nature of reality itself. One of the most profound implications of the EPR paper was the concept of non-locality. This concept is, to put it lightly, a head-scratcher, a conundrum that challenges our intuitive understanding of the universe. To get a grip on non-locality, let's talk about entangled particles. Imagine you have two particles and you entangle them. This means they become linked in a way that transcends space and time. Now separate these particles, put them miles apart, heck, put them on opposite ends of the universe. The crazy part, the state of one particle instantly influences the state of the other, no matter the distance. This is what non-locality is all about. It proposes that particles, once entangled, can be light years apart, yet they behave as though they are right next to each other. This is a direct contradiction to our everyday experience, where actions only influence nearby objects and any effect diminishes with distance. This is where Einstein had a problem. He believed in a universe where everything is local, where things can only be influenced by their immediate surroundings. It's the world we see around us, after all. He couldn't accept the idea that something happening here could instantly affect something happening there, with there being anywhere else in the universe. This is why Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, introduced the EPR paradox. They argued that there must be hidden variables that we're not aware of, which could explain these seemingly instant connections. They believed that quantum mechanics, as it stood, was incomplete, and these hidden variables would fill in the gaps. But quantum mechanics had a different story to tell. One of a universe that's interconnected in ways we can't easily comprehend. A universe where the spooky action at a distance, as Einstein called it, is real. This concept deeply troubled Einstein, but it opened up a new frontier in our understanding of the cosmos. Einstein famously referred to this as spooky action at a distance, a concept he found deeply troubling. Fast forward to the 1960s, when physicist John Bell entered the fray with a groundbreaking theorem. This theorem provided a way to experimentally test the predictions of quantum mechanics, tackling the deep-seated paradoxes that had been stirring up the scientific community. Bell's theorem is a cornerstone of quantum mechanics because it addresses the very heart of the Einstein-Podolsky-Rosen paradox. Bell proposed a set of inequalities, now known as Bell inequalities, that must be upheld if there are hidden variables at play, as Einstein suggested. But what are these Bell inequalities? Think of them as a mathematical boundary, a line in the sand that separates the world of hidden variables from the world of quantum mechanics. If an experiment's results fall within this boundary, it would suggest that Einstein was right, that there are hidden variables we've yet to discover. But if the results cross this line, it would affirm the strange, counterintuitive predictions of quantum mechanics. And so the stage was set for a series of experiments that would pit Einstein's deterministic worldview against the probabilistic nature of quantum mechanics. These experiments, which involved measuring the properties of entangled particles, consistently violated Bell's inequalities. The results were resounding. They confirmed the reality of quantum entanglement and challenged the idea of hidden variables, suggesting that the quantum world doesn't play by the same rules as the macroscopic world we're familiar with. In essence, these experiments unveiled a universe where particles, once entangled, could instantaneously influence each other's states, regardless of the distance between them. It was a revelation that shook the scientific community, confirming the non-locality of quantum mechanics and challenging the very fabric of our understanding of reality. These experiments pushed quantum mechanics into a new era, one where Einstein's determinism was seriously challenged. But as we'll discover in our next scene, this wasn't the end of the story. The quantum revolution was just beginning, and Einstein's skepticism would continue to shape its course. The philosophical clash between Einstein's determinism and the probabilistic nature of quantum mechanics was intense. Einstein's deterministic worldview held that the universe operates according to set laws, predictable and consistent. Quantum mechanics, on the other hand, introduced an element of chance, suggesting that at the microscopic level things occur probabilistically, not deterministically. The introduction of Bell's theorem in the 1960s and the subsequent experiments it inspired marked a turning point in this philosophical debate. These experiments showcase that the universe at the quantum level is inherently indeterministic. The results, which violated Bell's inequalities, confirmed the reality of quantum entanglement, thus challenging Einstein's belief in hidden variables and his deterministic view of the universe. This philosophical clash reshaped our understanding of the universe and continues to inspire debates among scientists today. As we delve deeper into the quantum world, we find ourselves navigating a realm that defies our intuitive understanding of reality, pushing us to rethink our fundamental assumptions. Despite his skepticism, Einstein's contributions to quantum physics are undeniable. This man, a titan of science known for his theories of special and general relativity, also played a significant part in the quantum narrative. Einstein's reservations, his probing questions, and the paradoxes he proposed in many ways defined the trajectory of quantum mechanics. They fueled debates and sparked curiosity, pushing other brilliant minds to investigate, test, and eventually validate the principles of quantum mechanics. His skepticism was not a rejection of the new physics, but rather a call for clarity, a demand for a more complete understanding. This healthy skepticism, this relentless pursuit of truth, is a hallmark of scientific inquiry. And so, while Einstein may not have reconciled with the probabilistic nature of quantum mechanics during his lifetime, his impact on the field is profound and enduring. And so we find that even in his skepticism, Einstein played a pivotal role in unveiling the quantum revolution.